Good morning, everybody. Experiment number 6 is formation of Jacobian elements. And in this particular lab syllabus, you are having Jacobian element formation only for PQ buses, network containing PQ buses. So let us go through the program. Already Jacobian elements calculation we have seen in Newton-Raphson method in the class. So straight away we go on implementing the same in this program. Initially, we start with clear instruction to clear all the variables. Capital Y is another variable which is used for input. Y is equal to input, enter the Y bus. We accept the Y bus of the given system. So already Y bus is developed for the particular network. So we take the input of that Y bus. Then in the next line, n bus is equal to input, enter the number of buses. So number of buses in the system will be taken as input here. Then this particular program is taken up for a particular problem or particular network. It's not in general form. This is another approach wherein you can straight away write the program for a particular problem instead of prompting the input. So this approach is followed here. So from the system, we get to know that bus number 3 is slack bus, remaining are PQ buses. As I told you earlier, this in this particular case we are not prompting for this data. Straight away we are taking it and using it. And then V of 1 is equal to 1 plus 0 I. Since bus 1 and bus 2 are PQ buses, their initial voltage will be 1 at an angle 0 or 1 plus 0 I as per flat voltage start. Bus 3 voltage is given in the problem, which is 1.05 plus 0 I. And this is a 3 bus system. From the given data, it has been taken. Next step, to find pcal and qcal. These are the variables used to find Pi and Qi, which are the injected bus powers, active and reactive, for I varying from 1 to n bus minus 1. So total number of buses in the system are 3, as we can see here. I is going to vary from 1 to n bus minus 1. So I is going to vary only from bus 1 to bus 2. This is because the third bus happens to be slack, so it will not be included in the calculation. So I is a variable which varies from 1 to 2. Vi is another variable used. Vi is equal to absolute of V of I. So we are taking the magnitude here. P cal of I is equal to 0. Q cal of I is equal to 0. Initialization is being done. Next, for K is equal to 1 is to n bus. K is going to vary from 1 to total number of buses. 3 buses are there. So it is going to vary from 1 to 3 in this particular case. Vk is equal to absolute of V of k. So we are taking the magnitude. You can see what is happening in every line that is being written on the right side. Delta is equal to angle of V of k minus angle of V of I. So delta is del k minus del I. Gik is equal to real of Y of Ik, which is nothing but conductance of the Y bus. See, when a Y is equal to G plus JB, so that G and B are separated here. This is done for off diagonal elements. So Gik is equal to real of Y of Ik. Bik is equal to imaginary of Y of Ik. Yik is equal to absolute of Y of I of k. Again, magnitude of Y bus is taken separately, saved it into Yik. Theta is equal to angle of Y of I of k. So that is nothing but admittance angles theta Ik. Then formula for P cal of I. You can see the formula on the right side. Pi calculated will be summation Yik Vk Vi magnitude cos of theta Ik plus del k minus del I. Straight away it has been implemented in the standard format. P cal of I is equal to P cal of I plus Yik Vi Vk cos of theta plus delta. See, for ease of programming, del k minus del I, already we have taken it as theta. Sorry, del k minus del I is been taken as delta here. So directly we can say theta plus delta. and q cal of I will be equal to minus minus magnitude of summation yik vk vi sine of theta ik plus del k minus del I. Same thing is written, q cal of I is equal to q cal of I minus yik vi vk sine of theta plus delta. This ends the subprogram. Then for I varying from 1 to n bus minus 1, that is it's going to vary from 1 to 2. Vi is equal to absolute of v of I, gii is equal to real of y of I comma I, bi is equal to imaginary of y of I comma I. So earlier we had done for off diagonal elements. Now here we are writing for diagonal elements. Gii is nothing but basically real part of yii. Y is equal to g plus jb. G is real part, b is imaginary part. That segregation was done earlier for off diagonal elements. Here we are doing for diagonal elements. Next, for k varying from 1 to n bus minus 1, vk is equal to absolute of v of k. Delta is equal to v of k minus v of I. You can see on the right side, delta is del k minus del I. Then gik is equal to real of y of ik. Bik is equal to imaginary of y of ik. Now here we try to implement the formulas for H, N, M and L. H, N, M and L are nothing but your Jacobian matrix elements J1, J2, J3 and J4. In order to avoid the confusion, we are using different alphabets here, H, N, M, L, instead of using J1, J2, J3, J4. So theoretically, when we solve the problems, we are going to use HNML. Here in the program, I have called it as J1, J2, J3, J4. So straight away, it is the implementation of the given formula. On the right side, you can see HIK is equal to magnitude of VI VK, GIK sine of del IK minus BIK cos of del IK. Same thing is written in standard format here. J1 of I comma K, VI VK, GIK sine of delta, because del IK is del I minus del K or del K minus del I, that is nothing but delta, minus BIK cos of delta. Similarly, NIK is nothing but your J2. MIK is equal to minus NIK. So J3 of I comma K is equal to minus J2 of I comma K. LIK is HIK. So L is nothing but your J4. J4 of I comma K is equal to J1 of I comma K. So in these 4 lines, what I'm doing is theoretically whatever is the notation we have used, I'm trying to compare it with the variables that we are using here in the program. So H is nothing but J1, N is nothing but J2, M is nothing but J3, L is nothing but J4. So these are the set of lines used for calculating Jacobian matrix of diagonal elements. Next we'll have to write for diagonal elements. So formation of diagonal Jacobian elements. Again, straightforward implementation of the formula. HII is equal to minus QI minus BII VI square. So you can see J1 of I comma I. Earlier you had J1 of I comma K. Now since it's diagonal, J1 of I comma I minus Q cal of I. We are just using the variable that we have called in this particular MATLAB. Minus Q cal of I minus BII VI square. Similarly, NII, MII, LII is taken as J2, J3, J4 for diagonal. Finally, your J matrix will be J1, J2 in the first row, J3, J4 in the second row. This completes your Jacobian matrix. So with this, I am concluding experiment number 6, which is a program for writing Jacobian matrix.